Thank you very much. Let me just unlock my computer, and we got some slides. And I want to get to the little demo I'm going to be doing at the end of this talk. So I won't take a ton of time to explain the context of what I'm doing. I'll just tell you that we're doing formal verification of smart contracts, so using the semantics of the EVM that was written by the people at Runtime Verification and the University of Illinois in Urbana-Champaign, which is a complete semantics of the EVM. It passes all of the VM and general state tests, and it has symbolic execution. And so it's really nice to do reachability proofs, which is what we need to do when we do formal verification. But in order to do formal verification, we need to actually verify something. So we need to have some sort of notion of what it is, what properties we're interested in verifying when it comes to smart contracts. And for that, we have developed a tool we at Dapphub called KLab, which does primarily two things. It allows you to specify in a neat format what you actually intend your contracts to do, and then it calls the K-framework prover to verify that this behavior actually is implemented in your contract. And then KLab allows you to step through these proofs, which are basically execution traces with symbolic inputs, and see how things are going, and if they went wrong, what happened. It also does gas analyzing for pretty much all of your contract behavior, so it'll keep things abstract as much as possible and generate a bunch of specs that you can analyze the gas behavior for your various functions of. So here's the specification format that we call ACT. So we see a simple token contract in like 15 lines here, and we're interested in verifying the transfer function, which just, I think you know what a transfer function does. So here is the behavior implemented, or expressed, I should say, in the ACT language. And the interesting part here happens in the storage location, where we refer to this this storage entry, which is the balances mapping, and we refer to the particular entry from the caller ID, and we give it some abstract value that it begins with, and then say that this value is going to be reduced by minus value. And all of the variables that we see here are real integers, so in order for this to be true, we need to make sure that they actually don't overflow or underflow, which is what we say in this if and only if condition. So from this, we generate a couple of specs. We take the if and only if block, and we generate two specs where we assume the conditions to be true, and one where we assume them to be false. And then if there's an if block present, we assume them in both of these cases. And in the end, we get 3 specs that are relevant to the execution. Here we do a gas analysis of the first time around here. We have like a rough estimate of how the function is going to behave, but we don't refer to the gas in a specific format. So let me show you what this looks like if we have a proof like this. So I've pre-run the execution. So let's begin by debugging the passing functionality. So it shows it that this execution took 3,000 steps, and these are not 3,000 EVM steps. They're actually slightly smaller, and I'm going to tell you why in just a second. But here you would have an interface that is familiar to you if you've used any debugger, where you can step through. You can have the source map to see what's really going on. And the thing that distinguishes this from any other debugger is that now you have these symbolic values on the stack. And they're going to be constrained in some manner. You can look at what the constraints are and see that they lie within the range of an uint 256. And you can step through to the end of the execution, and you can do a bunch of stuff. So that's kind of cool. But let's look at the fail case. So as I said, we have another spec that takes care of what happens here. And this one is slightly more interesting because it has branching. We can press B to look at the behavior. And now, since this is a fail spec, it's going to end in a bunch of reverts at a bunch of places. So if we go to the case here, this is when the from val is smaller than ABI value, which in this case we should of course revert because we don't have sufficient funds to do the transaction. And we see that if we step through here, we actually end in the revert opcode, which is what we ask for in the fail specs. So that's kind of nice. Let me show you something else. What we also have, if we forget about the behavior for 1 second, is that what we're actually doing here is that we're not only stepping through EVM steps, but we can actually look at all of the things that is being handled internally when we try to execute an opcode. We want to make sure that the stack doesn't overflow, that it doesn't violate whether we're doing a static execution or not, and then we're loading some necessary data, and then we're actually calculating the gas of the opcode, and we're checking whether memory is incremented. Then we need to check what particular flavor of the VM we're running, and we do all of these things. So in the end, it takes maybe 7 steps to go through a single opcode. And this is really useful, especially if you have some malformed code or something and you actually run into some stack overflow or some more internal errors of the EVM. Now, this rarely happens with well-compiled code, but if your compiler is broken, for example, this can happen. So I think that's all I'm going to display in the demo. We're working on a bunch of CI right now so that we can automatically take, whenever we've updated the bytecode, we can run it against our specs, make sure that we didn't violate any of the behavior that we have specified. And we're really doing most of the work right now to make sure that our specs are really exhaustive and cover the complete behavior of our smart contracts and make sure that everything that can happen is actually specified in our contracts. There's a couple of fun things that you can do once you have this. You can sort of forget about the implementation and say that the specification is actually what defines your decentralized application, and you can start to optimize for gas. You can rewrite your entire contract in Huff or whatever you want to do. You can have also like a bug bounty on the specs. So you can say like, these specs actually define the behavior of my decentralized application, and if you manage to write an implementation that satisfies the spec but is faulty in some magical sense, then we've screwed up in writing these specifications, and you should get some credit for that. So that was all of the slides that I had. So do I have some time for questions? Nice. Cool.
Questions? You said that the specification could be your application, but can you synthesize solidity from the specification, or do you have to keep maintaining the solidity as you change it? So in the general case, like you can specify things that you can't reasonably implement, since what you're really doing is like the specification is a little bit like a theorem and the implementation is like a proof. Formal verification is a little bit like Jeopardy, like somebody gives you a question or somebody gives you an answer and you need to ask the question of it. So like, of course, there are things that you can write in the specification that are going to be really hard to find an implementation of. But with most reasonable applications, you would be able to generate an implementation from it, presumably. And this is something that we have thought a lot about doing, and it would be really nice to get out EVM bytecode from the specification language. Thank you. Any other questions?
Hi there. Sorry, this might be a really silly question. But so from the sounds of it, so if you have if you have a specification for your smart contract that passes tests, then does the problem move from, how do I put this? There's no way of systematically evaluating the control flow of your program to determine if the specification is complete, is there? Because I'm guessing that's impossible, right?
Well, it depends on the particular contract that you're evaluating. Like if it's a complete arbitrary piece of code, then of course it's going to be impossible to evaluate. But in the most reasonable cases, we have some fairly finite state machine that we're interested in describing, and then we can actually reach exhaustiveness.
Okay, cool. Thanks.
All right, let's bring up our next speaker and thank Martin.
Thank you.